Welcome to qnawire.
This is problem 18 of chapter 23. For this problem, we're asked to draw a ray diagram for light going through air. So here we are starting at air. We're going to denote that by N of air. This is going to be the refractive index of air, which is 1. Then it's going to pass through some film here. So we're going to call this N film. And we could assume that that refractive index is going to be greater than that of air. And then light is going to come from the air, go through the film, and then come out into air again. Okay, before we start doing the light diagram, let's recall certain things. As light goes from a refractive index that's from low to high, there's going to be a pi shift, or there's going to be a phase shift of pi degrees, or 100 of pi radians, or 180 degrees at the boundary. So if light is coming in this example, from air, and then it hits the boundary, what gets reflected off of the boundary, since we're going from an air equal to 1 to a refractive index greater than 1, it's going to be shifted 180 degrees. So what comes out is going to be shifted 180 degrees, like so. When the light goes through into the boundary, it's going to be refracted, but since this is a thin film, we could disregard that refraction, and we could just treat the distance traveled by the light, we could treat it as the thickness of this film. So that thickness, we could call it T for the thickness of the film. So let's go ahead and label that thickness here T. So the light, let's go ahead and draw the diagram. The light is going to be coming in here. Since it's going from one refractive index to another, technically this is going to go ahead and refract, but since it's a thin film, we're just going to treat this distance here T. Then it's going to reflect here, a portion at the boundary is going to reflect. This reflected ray is going to be shifted by 180 degrees. So let's denote that. So that's going to be, if there's going to be a phase shift there, so let's call that delta reflected. And that's going to be reflected by 180 degrees. If a wave is shifted by 180 degrees, that means, so if we have a wave like this, and let's say another wave is in phase with it, so it isn't shifted, these two waves would interfere constructively. However, if a wave is shifted by 180 degrees, right, you could imagine taking this and flipping it here over some x-axis. If we flip it over by 180 degrees, notice that this peak would interact with this valley, and they would cancel out. There would be destructive interference. So another way of saying a shift of 180 degrees, we could call that a shift by lambda over 2. Because by shifting the wave by lambda over 2, we achieve the same effect where valley, right here, this valley would interfere with this crest, and you would also get destructive interference. So we could call that path length difference. Of course, the path length difference corresponding to the phase shift, we could call that lambda over 2. Okay, so light is going to come in, it strikes the boundary, it gets shifted by 180 degrees. That corresponds to a path length difference of pi over 2. It's going to go through this material, and then a portion is going to reflect from this material. Now, is this ray going to be shifted by 180 degrees? Well, as light is in the film, it's going from the film to the air, so it's going from a higher refractive index to a lower one. So the only time you get shift of 180 degrees, let's write this out. You get a shift of 180 degrees if n1, if you're going from a lower refractive index to a higher one. So if we're going from this, if n1 is less than n2, and we are going from n1 to n2, we're going to get a 180 degree shift. If we're going from n2 to n1, we're not going to get any shift. So we write that as 0 degree shift. Nothing gets shifted. Okay, so in the first case here, this first reflection, we're going from low to high, so we get a 180 degree shift. Once we're in the film, we're going to go from a high refractive index to a low one. So this, what gets reflected here, experiences a 0 degree shift. So the light that comes in, it gets transmitted, and then it reflects. This one is not shifted. Okay, so while it's in the film, though, there is a path length difference between this reflected ray and this one that's going to reemerge out of the film. When this ray gets reflected, again, it doesn't experience a shift, and then once it meets the boundary, again, it's going from a high refractive index to a low one, so high to low, 0 shift again. It's not going to be shifted anymore. So far we've only have one lambda over 2 shift, or path length difference of lambda over 2. But we also have another path length difference because it goes down here and then it gets reflected. So the total path length difference, let's call that delta, it's going to be equal to the path length difference due to the reflection, right? The path length difference that can be represented by this lambda over 2 due to the reflection, and the path length difference in the film itself. So let's call that delta t. So that's what's going on here. The next part of the question is asking what condition would have to be met such that an observer here would see no light for a given wavelength. If there's going to be no light, that means that the light emerging from this transmitted ray, then reflected, then coming out through the film, must have to destructively interfere with the ray that was initially reflected here from the light. So this ray coming out here must destructively interfere with the ray here coming out from the bottom. So how are we going to express that? Well, the net path length difference, it has to be an odd integer multiple of half wavelengths. So in this case, this is going to be for destructive interference. For destructive interference, we have the path length difference of this first ray and this. So the ray that goes through and comes out, that one's not shifted at all. So this ray here, the net path length difference, if we account this shift and then the path length difference is going to combine to form this net path length difference, must come out to be an odd integer multiple of half wavelengths. So here m is going to be equal to 1, 3, 5, and so on. Now, delta reflection, right? At this boundary, the wave gets out of phase. It gets shifted by 180 degrees. So instead of writing that, we're going to describe that shift by lambda over 2. So that's already an odd multiple of half wavelengths. So the only way this odd multiple of half wavelengths could be added with delta t to give us an odd multiple of integer wavelengths, that implies, okay, so let's write this out. If lambda over 2 plus delta t is going to give us an integer multiple of half wavelengths, that means delta t must be an even multiple. Well, it could also it just has to be an integer multiple of wavelengths. So we get the following results. We get delta t must be an integer multiple of total wavelengths. So if delta t is an integer multiple of total wavelengths, and then we tack on half a wavelength, that's going to be that sum is going to be an odd integer multiple of half wavelengths. So delta t would be m times lambda, where m is any integer. So in this case here, let's go ahead and copy this. In this case here, m would be equal to 0, 1, 2, 3, etc. Because if delta t is equal to an integer number of wavelengths, and then we tack on half a wavelength, the net result is an odd integer multiple of wavelengths. So for example, let's say this was 0. If we set m here equal to 0, we just have 0, 0 plus lambda over 2. It's an odd integer multiple of half wavelengths. How about if m here was equal to 1? If m here was equal to 1, we have lambda. Lambda plus lambda over 2 is 3 lambda over 2. So again, we have odd number of half wavelengths here. So this is satisfied. Now, what is delta t? That's the path length difference associated with the light going through the film. So delta t is just equal to 2t, because that's the distance traveled by the light as it goes through and out of the film. The film is thin enough that even though it's not exactly t, as the film gets thinner and thinner and thinner, these diagonals become approximately t. So that's what we're calling it, 2t. However, as the light goes through this film, its wavelength changes. So we are going to express this 2t in terms of the wavelength of the light in the film. So n film is the refractive index of the film, and this is defined to be c over the speed of light in the film. So let's call it v film. When we solve for v film, here we get v film is equal to c over n film. But this is going to be the wavelength of the light in the film times the frequency. The frequency is the same in the air as it is in the film, because the frequency is determined by the sound source. So here we could go ahead and express this expression here. We will express this c. C is given by lambda f over n film. And this lambda film times f, that is how velocity is expressed. So let's take a look at these last two terms here. Notice that f cancels out with f, and we have an expression for lambda film. It's going to be equal to lambda over n film. So here, this m times lambda here, this is actually going to be we are going to actually express this 2t. Let me replace this. We're going to actually express this 2t in terms of lambda film here. So remember what we said before. In order for this to occur, there has to be an integer number of those wavelengths in the film. So this is going to be m lambda film. Because as the light goes through the film, the wavelength changes to lambda film. And how do we express lambda film in terms of the original wavelength outside in air? Well, we just did that, so that's going to be 2t is going to be equal to m times lambda in the air over N film. So in order for destructive interference to occur, the thickness must satisfy this equation. The thickness must satisfy the equation m lambda over N film, where m is 0, 1, 2, or 3. So there was a change as we went from this m to this m. Okay, so these m's are not the same. These m's are not the same. Let's just go through it one more time just to make sure that there's no confusion between those two m's. Light comes, bounces off of it gets reflected off. That reflected part is shifted by lambda over 2. It's shifted because we're going from a lower refractive index to a higher one. The transmitted part of the beam is not shifted, and then as it reflects here at this boundary, since we're going from a higher refractive index to a lower, it also doesn't get shifted. We're going from higher to lower, and then it comes out and through. The net phase shift can be represented by the phase shift occurring at this reflected part and by the path length difference associated with the light going through the film here, delta t. For destructive interference to occur, that combination must come out to be an odd integer multiple of half wavelength. So we represent that by an m here, so 135 odd integer multiple here. However, delta reflection is already an odd integer multiple of half wavelengths. So that means delta t must be some integer multiple of wavelengths. But we are in the film, so that wavelength is lambda film. So here we solve for lambda film. And here it's going to be an integer multiple of lambda film, so that's why it's m0, 1, 2, 3, and that's where that shift occurs between m's. Here where it's odd numbers, and here where it's 0, 1, 2, 3, so the consecutive integers. Then we go ahead and delta t, the path length difference is 2t because it bounces, it goes one way and then comes out the other way. Then we go ahead and substitute lambda film for lambda over N film, and then we solve for t. So if the thickness of the film satisfies this equation, where lambda is the wavelength of the light in air, N film is the refractive index of the film, and m is any integer 0, 1, 2, 3, etc., then there would be destructive interference on this side. This concludes problem 18.